Hey there, thanks for joining me for examples 6.6.4 and 6.6.5. 6.6.4. We're told that A and B are 5 by 5 matrices, such that the determinant of A is 3 and the determinant of B is 4. We're asked to evaluate the determinant of 2A transpose B inverse A. So we're going to start by applying some properties of the determinant. So the determinant of 2A transpose B inverse A, the first thing we can do is pull out this constant, but we can do that only if we raise it to the power of the size of the matrix. So that's 2 to the 5 times the determinant of A transpose B inverse A. Now 2 to the 5 is 32, and then we can use a property of determinants that if we have a product, we can split up that determinant as the product of determinants. So determinant of A transpose times determinant of B inverse times determinant of A. Next property that we have is that the determinant of A transpose is equal to the determinant of A. So determinant of A times, and then we've got the property that the determinant of the inverse is 1 over the determinant of the original matrix, so 1 over determinant of B, and determinant of A is already given. So we have 32 times determinant of A is 3, times 1 over determinant of B is 4, times 3. We can simplify a little bit. 32 divided by 4 is 8. 8 times 9 is 72. Example 6.6.5. Now we're asked to find all possible values of determinant of A if A is a skew-symmetric or anti-symmetric n by n matrix, and two cases. N is either odd or even. So the first thing we should do is remind ourselves of what a skew-symmetric matrix is, and that's a matrix whose transpose is equal to the negative of the original matrix. Now, we were asked questions about the determinant, and there is no determinant to be found, and so we can introduce one. We can take the determinant of both sides of this equation, and so determinant of A transpose is the determinant of negative A. And we can apply some properties, just like we did in the previous example. The determinant of A transpose is the determinant of A. And we can bring out this minus, it's like a minus 1, so we can raise that to the power of the matrix, which is n, times the determinant of A. And now we're going to split this into the two cases. If n is odd, then minus 1 to the n is equal to minus 1. Which means that our equation becomes determinant of A is equal to negative determinant of A. Now there's only one number in the world that has that property, but if you don't see it, we can add determinant to both sides, and so we get 2 times the determinant of A is equal to 0, divide, and determinant of A equals 0. Second case, what if n is even? If n is even, then minus 1 to the n is equal to 1, which means that the equation above becomes the determinant of A is equal to the determinant of A, which, while true, gives us no information, right? We have no information, and so that means that the determinant of A really can be any real number.